Welcome to Data Skeptic, everybody, in our continuing series on natural language processing. This week we have another in-depth dive on a particular use case of natural language processing, authorship attribution. This, as you might have guessed, is the task of taking a document and then, from previous examples, being able to establish who is the author of this document. Sounds pretty straightforward when you say it, but as you can imagine, this is no easy task. Yet interestingly, think about the writings of someone close to you, a spouse, a friend, a family member. Very likely you could have a high probability of picking out which documents or text they wrote versus ones written by somebody else. How are you able to do that exactly? And more importantly, how can we get machines to do the same thing, only better?
My name is Elisa Ferracane, and I'm a fourth-year graduate student in the Department of Linguistics at the University of Texas at Austin.
Could you tell me a little bit about your focus in grad school?
I am in the linguistics department. Since I have a background in computer engineering, I'm also interested in computational stuff. So my focus is on computational linguistics, and more specifically on computational discourse.
And I think the project of author attribution sort of speaks for itself, but in case anyone's not familiar with it, can you tell us what authorship attribution is all about?
So the task of authorship attribution is you're given a set of authors and you're given a set of texts. What you have to do then is, given a specific text, you have to figure out who wrote that document from that pool of authors that you have.
And what is it traditionally used for? Is this for like forensics and police activity or historical documents? Why do people have an interest in attribution?
Sure, it can be used, like you said, for forensics. I think there have been some cases where it's been used for forensics. Also for trying to figure out who wrote certain historical documents and maybe who wrote certain pieces of literature many, many years ago.
So it seems like it wouldn't be an exact science. What are some of the challenges in approaching a problem like this?
The way it's used in the real world versus the task that we're looking at is maybe a little bit different, in the sense that when we're looking at it in a very well-defined task, you have a set of texts that you're looking at. So you've already narrowed it down to, okay, these are the specific texts that I'm looking at. And you've also narrowed it down to, these are all the specific authors that I'm looking at. The specific authorship attribution task that I'm looking at is maybe an easier version of what somebody might want to do in the real world case. In my case, because we want to use data that's publicly available, we don't want to have to pay licenses to any authors that have books out there. We look at the Project Gutenberg, which is a pretty sizable data set that has books written in the 19th, 18th century. Obviously, they don't have licenses anymore. We downloaded a set of 50 books from Project Gutenberg. That was one of the data sets that we looked at. Those 50 books that we chunk into smaller pieces and then look at the authors. And the other data set that we look at are movie reviews. So this is a little less traditional in the sense that these are very short text, but it's also relevant nowadays because those kind of medias are pretty widespread.
Absolutely. Well, in the beginning parts of your paper, you'd mentioned some of the more traditional ways, like the stylometric features that people have used in the past. Before we get into the innovations that the paper presents, can you tell me a little bit about the background techniques people have been applying?
Different authors use punctuation differently, for example. And so that's an easy way to figure out, oh, that's Charles Dickens, because he usually puts a comma in between his noun and verb, which was fairly common back in those days, the use of punctuation to denote pauses, as opposed to nowadays, it's a lot more rule-based. People look at punctuation, also look at the words themselves. Certain authors use certain words a lot. So these are a lot of the stylometric cues that people have often looked at and what we refer to as surface level cues.
Got it. And what are we missing by only looking at the surface level cues?
Discourse, of course. How does an author develop their story? Is that something you would think it would be common across different pieces of text that the same author writes? The specific kind of discourse we looked at is basically looking at the entities, the characters in the story, for example, and how they develop and what kind of role they're playing in the discourse and how that evolves over the sentences and over the story.
I don't know if the listenership will all share one common experience of we've all read a certain book or anything like that, but could you maybe, through example, take a popular work of fiction and give a few anecdotes about what that looks like, from beginning to end in a story?
Specifically in our paper, we actually don't look at the entire novel. So an entire novel would be hundreds of pages, and it's not something that a neural network would be able to process. So what we do is we chunk them into much smaller pieces. So I can talk about maybe what happens in a much smaller piece of text. One example, and it's not necessarily indicative of a specific author, but it gives you an idea of what we're trying to capture with the discourse. As an example, you can think about there's a story about a person is narrating a story about their father, and it talks about who their father is. And then they introduce the mother. Now, at the beginning of the story, the father is in the subject of the sentence. It's a primary entity.
Mm-hmm.
And then they talk about the mother in a secondary role. So maybe talk about the mother in the predicate of the sentence. So maybe they're a direct object or an indirect object. As the story is evolving, the focus is now going to shift away from the father, and it shifts back to the mother, which is the more central character in the story. What the author does then is, in the following sentences, they start talking about the mother first in the role of the subject of the sentence, the grammatical subject. The father is still there in the sentences, but now he's being referred to in the predicate of the sentence, maybe as an indirect object. As the story is progressing more, then you see the father doesn't appear, but the father has now dropped off from the following sentences, and it's now more about the mother.
Interesting. And will different authors use different genders you're going to look at, or different like time series of how that develops? What makes someone's writing unique from someone else's in this regard?
That was our intuition, that different authors would use different ways of developing what we call salient characters or salient entities.
Mm-hmm. And is it what you ended up finding? Did the data meet the expectation?
So it did meet the expectation in the sense that once we added these features that are capturing these changes in entities, our performance increases. So we do better at authorship attribution. We looked at two ways of how the discourse changes. The one that I described in my example was looking at how the grammatical role of these entities changes across sentences. The other thing we looked at was how does the discourse relation of that entity change across time. When I talk about discourse relation, then we kind of have to introduce another concept. So we specifically looked at this discourse theory called RST, which is short for rhetorical structure theory. In a nutshell, the goal of RST is to analyze a document by cutting it up into little pieces that they call discourse units, and then trying to relate each discourse unit, see how they're related to each other. What kind of discourse relation would unite each pair of discourse units? And then you end up forming a whole tree, a whole discourse tree over the entire document to describe the discourse of this document. And the nice thing about looking at discourse is that you're going now beyond the sentence level. You can look at discourse within the sentence, but you also want to look at discourse beyond a single sentence. So if I said, for example, I quit my job because the hours were too long, that's just one single sentence. And there's two clauses. I quit my jobs. There's a first clause, and then the second clause is the hours were too long. And it's pretty obvious to you that the relation between these two clauses is a causal. And there's a strong cue, the word because, that tells you that one thing happened because of the other thing. And so that's an example of a discourse relation. And that's really easy to spot. Now, there's lots of ways that you can say that same statement. Instead, I could break it up into two sentences. I could say, I quit my job, period. The hours were too long. There's no because anymore, but you would infer just because one sentence is next to the other, just because they're adjacent, you infer there's a causal relation. That discourse relation still holds between those two pieces of information. And so that's what we want to try to capture with RST, with these discourse relations.
So yeah, I have some sense, and a better sense having read the paper, of the linguistical data structures you're creating. How do then those become useful to the machine learning part of the process?
We'll basically try to get out all these discourse relations between these salient entities. From that, we'll get a sequence of discourse relations that happen across the document. And we'll plug that in as additional features for our neural network that's going to be learning the authorship attribution task. In our paper, we experiment with lots of different ways of how do you add in these discourse features. And what we found was that if you just have a kind of a global view of how the discourse relations are changing across the entire document, not just like between sentence pairs. If you look at how the discourse changes across the entire document, that gives you the biggest boost for the authorship attribution task.
Interesting. Why do you suppose that is?
I think that's because a lot of the stylometric cues can capture stuff at the local level within a specific sentence, but where discourse really shines is when you're going beyond the sentence level. And not just pairs of sentences that are adjacent to each other, but let's take an even more global view, and that will capture more discourse.
With regard to the neural network then, can you tell me a little bit about how you went into the process of experimenting with different types of algorithms and how you settled on the one that you came up with?
We decided to use a CNN convolutional neural network, in part because we knew some prior work showed that CNN do really well on authorship attribution tasks using these surface level cues. We figured let's start with a really high performing neural network. Once we introduce discourse, if we have a not so great neural network, then you might argue the only reason discourse gave a boost is because your network was underperforming to begin with. So we thought, let's have a really strong baseline and start with that. So we started with a convolutional neural network. Now that we have a neural network, we should take advantage of that and do embeddings instead of just a probability vector. So that's where we went next. And it turns out that using the discourse embeddings instead of this probability vector, the discourse embeddings work the best.
So I have a picture in my mind of some of this discourse data is like those trees you were describing earlier of the relationships across the whole document. How does that turn into the raw mathematical vector of features that you feed to your neural network?
The first thing you want to understand is what is an entity grid model. And that was something that was introduced a while ago by Barcel and Lapata in 2008. Basically, they create a grid, a series of like just a table. Each column is an entity that you see in your text. And each row is a sentence. They marked on this table where each entity showed up, in which sentence it showed up, and then what was the grammatical relation. That is it acting as a subject or an object or something else? So they would fill up this entity grid. From there, what they would get was a table of all the entities and what roles they were assuming in each sentence. From there, they looked at sentence pairs. So they looked at how would a particular entity change from one sentence to the next. The father went from being a subject to an object from the first to the second sentence. And then it went from an object to not being there at all from the second to the third sentence, and so on and so forth. So they have all these transitions from one sentence to the next. And then they calculate all the transition probabilities across the entire grid. And then they come up with this probability vector. We use the same entity grid idea, but instead of populating them with grammatical relations like subject, object, we populate them with the discourse relations. The key being that this entity grid model is built on having these salient entities, which means that we need to have a good coreference resolution system. And we might touch on that later, but it does rely on having texts where there are entities that are mentioned at least 2 times throughout the story and mentioned in a way that an automated coreference resolution system will actually resolve it. Coreference resolution is a very challenging task. So there is definitely lots of room for improvement for coreference resolution.
And can we delve into that a little bit? I don't know that all the listeners will be familiar with it.
Coreference resolution, I can give you an easy example first. I can tell you, Jim went to the store today. He bought some milk and bread. Who does he refer to?
Well, Jim, of course, in this case.
Right. Okay. And that's it. You did coreference resolution.
All
so
right.
You're trying. So that's an easy example of coreference resolution. Let me think of a harder example. Mary told Jane to go to the store. She didn't want to go. Who is she referring to?
Well, I feel like it could go both ways, but I presume it's Jane who's the one who's actually going to go.
I don't know. There isn't a right answer.
Yeah, maybe Marie forced Jane to go because she was the one who didn't want to.
I mean, you could argue it either way.
Yeah.
You could say maybe you can keep reading about the story and figure it out from there.
Right.
But for just giving those 2 sentences, it's pretty ambiguous.
Are there off-the-shelf solutions you can get the same way we can do part-of-speech tagging? How does one go about approaching coreference resolution?
There is what we use, and I think that a lot of people use, is the Stanford Core NLP, Coreference Resolution System. It reaches near state-of-the-art. It also includes a whole bunch of other functionalities like part-of-speech tagging and so on and so forth. So if you want that specific functionality, then Stanford Core NLP is one of the big options that you can go to.
So after you've built the network then, how do you evaluate its success? What can we point to in terms of metrics and talk about the quality of the model that was produced?
To evaluate the authorship attribution task, we look at the F1 results. So that's averaged across all the authors. So we measure F1, which is the harmonic mean of precision and recall. And that's how we evaluate the task.
And so we could talk about F1 scores. They're always sort of out of context in a way. But can you share yours, and maybe are there any benchmarks we can compare to?
We compare when we're looking at the smaller data set that I haven't mentioned yet. This is a set of Gutenberg novels, only 9 novels. And the reason why we chose that data set is because prior work looked at that also. So basically, we compared to prior work on this 9 novel data set. We can see what the F1 scores are, and you can kind of get an idea of what the numbers were before and after. So our numbers are roughly, they start out for the prior work, they're like in the 80s. And then for our work, they go high up into the high 90s.
And do you find that that's approaching sort of the upper limits of what's possible, or is there, a ceiling to that F1 score that human levels can be achieved with more and more methodology and research?
I think the task is basically maxed out now. I think it's time to introduce harder data sets or bigger data sets.
Well, could you talk a little bit then about your experience with the movie reviews that you'd mentioned earlier? How did the approaches from novels, which are, usually grammatically correct and well-structured and things like that, to a new domain of probably much shorter documents that may not have the sophistication of language that we expect out of novels?
So in the novels dataset, we found that adding any kind of discourse would help, like whether it was using the grammatical relations or using the discourse relations, and then either that probability vector or else these embeddings, and whether we were using local or global, they always helped. When we go to the movie reviews, we instead find that there's only one flavor of our network that is able to outperform the baseline significantly. That's the one with the discourse embedding as a global view. When we look at our entity grids that we had constructed, that's kind of where our whole discourse relies on, is finding these salient entities. We basically see that there aren't a lot of salient entities, but more importantly, the coreference chains that it finds are really short. So maybe an entity will show up only once in a sentence and then it'll never show up again. So these are information where we're going to pull out all the discourse from is just very sparse. There's very little to go on, which kind of would motivate you to then get discourse through a different means that doesn't necessitate resolving co-reference chains. There are co-reference chains. There are some, because otherwise we wouldn't have gotten any kind of performance benefit at all in any of the cases. But partly the documents are short, and partly co-reference resolution is a hard task. It's even harder in this non-typical domain where you have more informal writing, and probably the co-reference resolution system itself is doing pretty poorly.
And in comparison to the novel set, what sort of F1 scores did you guys see?
They were in the 90s, but not the high 90s, more like the low 90s.
Wow, so this seems awfully effective at authorship. I'm a little surprised because I've often felt like that there's so much variance in my own writing, whether I'm typing something technical or something to a friend, that it would be difficult to pin me down and say, Kyle wrote this. Is it that you're working on a more specific domain that makes this possible?
Very likely, because if you wanted to do this for yourself, you would have to take let's say, all the emails that you're writing to your friend.
Mm-hmm.
That would be the whole set, everything that we would be looking at. We wouldn't be looking at when you write to person X or when you write something more formal writing. It's all in the same, like you said, all in the same domain. For the movie reviews, there's one author writing lots of different movie reviews. So they're all writing the same in their minds. They're using some kind of template.
I see. Yeah, that makes a lot of sense. So maybe to wind up, I wanted to ask you a little bit about the interpretability of your network. Not that that's a requirement. If it performs and we have an empirical result that's useful, that should be good enough in a case like this. But what are you able to learn about how the discourse features have influenced the network, or the types of features it relies on? Basically, what do you know about your model?
Right. And that's a good question, especially for neural networks. We did not use any attention, and that's something that is very beneficial when you want to try to analyze what your network is doing, but we don't have that here. So what we did was we looked at t-SNE embeddings to try and understand maybe how the discourse embeddings are clustering in the space. We did that analysis. We weren't able to really draw any conclusions from that. So what we looked at instead was the confusion matrix. So we tried to analyze, where does the network go wrong when it has the discourse? Where does it go right? And then compare that to the version of the network where there is no discourse, and then see, oh, look, once you add in the discourse, then suddenly this author performs much better than it did without the discourse. And so then we can kind of make inferences about why that might be. When we make those kinds of inferences, it's less of a hard science, I guess.
Sure, yeah. The Gartner Data and Analytics Summit is taking place in Orlando, Florida, March 18th through 21st. Some of the topics this event is going to cover are AI, machine learning, Internet of Things, digital twins, data science, advanced data analytics, pervasive analytics, and data governance. Here's a sampling of some of the events on the program. All right, my first pick is Ask the Expert. So you want to be a CDO. Second pick, Blockchain for Data Management. How the world's worst database will work for you. Third pick, the impact of VR, AR, and MR on data and analytics. We'd be here all day if I went through the full list. Learn about the BI bake-offs, the innovation panels and the forums, and everything else about the conference by visiting gartnerevents.com/dataskeptic. Once again, that's gartnerevents.com/dataskeptic.
My name is Su Wang. I'm a PhD student in computational linguistics at University of Texas at Austin. This is my fourth year, and my research lies in the intersection between semantic inference and neural network architecture designing.
Well, welcome to the show, Sue. As you know, I've been talking to your co-author, Elisa, about the paper you've written. We're just getting back from the break, so would you mind giving people a refresher on what is authorship attribution?
When you talk about authorship attribution, it's actually, there are different approaches to this. It's a text classification task, but it can be done supervised or unsupervised. In the supervised setting, you are given a bunch of label texts with their authors as the labels. And what you are trying to learn is a mapping from a text and an author, right? That's the supervised setting. And in the unsupervised setting, what you are trying to learn is a clustering algorithm with its learned parameters that could help you characterize the writing style of a particular author. You might not know who this author is, but you know these documents, this particular set of documents are written by one single person. So that's unsupervised setting. So I'm talking about this because apparently the success means different things for these two settings, right? In a supervised setting, you want to get as accurate as possible, right? Basically, it's just accuracy, right? And a sort of, which I think is more important measure of success is how much you understand what the model is doing after the model is being able to achieve a high level of accuracy, right? The model also has to be interpretable. For unsupervised authorship attribution, I haven't done a lot of work on this, but I've done related work in coherence and semantic inference. Basically, what you want to learn is stuff like how does this individual organize a narrative? How does he or she lay out a narrative? How does he talk about things? And how does the person reason about topics? In my opinion, the more we can understand a high performance, that's the sort of the assumption, right? The sort of the first thing you have to do. The model has to perform well, and then to understand why it does what it does is really important.
I suppose that's universally true in almost every application of machine learning. But whatever approach you take to author attribution is sort of an elected methodology. Some critic could always point at the method and say it's not applicable or something. How do you arrive at a certainty that you're going about it the right way?
That depends on what's at stake, right? If you are working in medical field, the level of understanding you need before you push a product would be higher, definitely higher than other fields. In general, I think to be able to understand the model, to make it more interpretable sort of serves well for researchers in the field, for sort of academic interest. It also sort of stimulates future research because you've seen a lot of works these days where you have these different LSTM, different sort of wired up CNNs stack up together, getting more and more complicated, but the level of understanding is limited. And people make incremental improvement on established tasks, but to me, sort of in my mind, that's not really very interesting.
I think the use case of authorship attribution is pretty intuitive. You've got some document and you'd like to predict who the author is. Most listeners will get that, but I'm not sure if they will have encountered the idea before. Do you have any examples of academic or industrial applications of these methods?
What I know is it's definitely applied in forensic science, right? One of the first uses, like the Federal Papers, right? The famous case. There's also plagiarism detection, which I think is a big part of this. Other than that, authorship attribution for me is a way to understand semantic inference, basically. I'm using it as a vehicle to study semantics.
So there's a long history of different ways people have tried to do author attribution, and as machine learning has matured, so have a lot of those methods. Why were neural networks the right choice in your project?
So this research grew out of a term paper, right? We're doing this term paper, and it's an interesting story. So the professor showed us two papers over the 30 years when this course has been offered at UT. Only two papers are published, and the professor sort of challenged us. This is Ray Mooney we're talking about, and he said that see if you guys can write something that's actually publishable. So what we did was we went out to basically tried all the neural architectures. Like you said, it's a hot topic and lots of people care about it, right? So we tried a lot of things on it. Basically a massive scale grid search to look for what hyperparameter setting and what architecture works well for this particular thing. We tried the usual suspect from the simplest logistic regression to SVM and LSTM CNN, of course. we were also helped by these wonderful research, previous work on the topic. There's a paper I cite a lot in this work, which is Stresha 2017, and there's a Ruder et al. 2016. In these works, they've done a lot of work to survey different architectures. We ended up choosing CNN to basically strike a balance between performance and speed. We were given 2 months to complete the project, right? This is very similar to some of the industrial settings. Previously, I interned at a startup local in Austin, typically you are given a problem. You have to solve it in a limited amount of time. It has to be pushed to the next step in the production. Having a fast model that you could experiment and optimize is very important. So in the actual experiment, I've seen people reporting that LSTM performs the best, right? So that was the first thing we tried. It did. Indeed, it worked, well, in absolute performance, it worked better than CNN. But there's a problem with the particular task we're working on, which is we're reading very long texts. We're talking about thousands of words. Because of the sort of parallelability limitation for LSTMs, it's very hard to run a fast sort of experimental cycle, and it's also slow in inference time. If you are doing sequence-to-sequence translation, that might not be a huge problem. With LSTMs, usually it would do better than CNN, but it was a problem for us, so we settled with CNN. Let me qualify my previous comment about CNN. So it doesn't apply sort of universally to all cases where, LSTM always performs better than CNN, and CNN is always faster than LSTM. But, if performance is an important thing, then I've seen work where CNN can actually perform comparably to LSTM, like this one paper by et al. 2018, where they proposed a temporal convolutional neural network. So this is a stacked layers of convolutional layers, and you have this dilated structure that helps you to cover sort of long distance dependency. In that particular work, CNNs were found to be just as good as LSTM, but only over 10 times faster. In this particular work, there was one architecture we didn't get a chance to experiment with, big regret to both of us, which is the transformer encoder. This is Vasvani et al. 2017 popular transformer sequence-to-sequence. Attention is all you need. That's the title of this paper. So you don't have the intermediate, latent encoding of your structure, and you have this sort of stacked multi-attention plus feed-forward layers. Very simple architecture, very parallelizable. I've been using it frequently in my research. The good thing about it is it's just as expressive as LSTM, as powerful as LSTM, only with the speed advantage. So this was the thing we sort of regret that we haven't tried.
Can you tell me a little bit about the feature engineering? What are you training the network on exactly?
So we tried two types of features. So the first type we tried is the grammatical relations, which is the original method proposed in this entity grid paper, Barzilai and Lapata 2008, where you have a sort of matrix-like data structure where your rows are your sentences in a sequence in which they appear in the text, and your columns are entities. For example, any noun could be an entity, right? A Microsoft or father or mother, something like that could be entities. A grammatical relation feature would be, for example, you are at sentence 1, you're looking at the entity Microsoft. It appears in the first sentence as the subject. It appears in the second sentence as the object. Then the feature you have would be a subject to the first cell and an object to the second cell, right? We have 4 different types. You have a subject, object, or other arguments. These are, we call it obliques in linguistics. Basically, if you have something like, I have ate a burrito that's old, something like that. This relative clause that follows the main clause, which is that is old. That could be treated as sort of an auxiliary argument in this whole event, right? So if it's not the subject and it's not the object, but it is one argument of this event, we're treating it with another label X, or it's none of that, which we just treated with a separate label. These are grammatical relation features. By having this matrix data structure, you are able to track how the entities sort of flows across the discourse. So that's the first type of feature we tried. The second type is discourse relations. This RST, discourse theory, rhetoric structure theory, where suppose you have two clauses. These are called elementary discourse unit, right, or EDUs. Let's say that you have two sentences, which the first sentence is, my father was a clergyman. I'm citing an example from the paper. My father was a clergyman of the north of England. And the second sentence is, who was deservedly respected by all. So in this particular pair of sentences, their relation is labeled as elaboration. So the second sentence is an elaboration of the first sentence. The first sentence mentioned this fact that my father is doing something, and the second is, elaborating on my father, this particular entity in the previous sentence. So we have these discourse relations like elaboration, given an example, or sort of two facts juxtaposed side by side to describe how a discourse is structured, basically. We use this idea and integrated these features into this sort of entity grid like a matrix. Again, you have your rows and your columns. So your rows would be sentence pairs. These are sort of sentence bigrams. Sentence 1, sentence 2, sentence 2, sentence 3. And in your cells, you would have their discourse relations, right? The second sentence elaborates on the first sentence. The third sentence gives an example of the second sentence, like that. So we have these two types of features. Then we process these matrices and extract features, let the neural model to learn the features, and we use the features to sort of map them to a distribution over author labels to give prediction.
I know you experimented a little bit with different algorithms and different corpora. Can you share a summary of the results you had through these efforts?
We used the 3 data sets for evaluation. The first data set is previous work. So you always go to the previous state-of-the-art to see how well you do there, right? So this is the original Feng and Hurst 2014 paper, where they have a small corpus of 19 novels and 9 authors. And we want to sort of get a benchmark or baseline where how well our model does. And the second is an extended novel corpus. It's basically of the same type as the Feng Hurst 9 novel corpus. We only extended it to 250 novels from 50 authors, right? So we're trying this data set because we want to know if a neural model, which is known to be data hungry. We want to know if we give it a lot more data, would it clear even larger margin over non-neural models, right? Simpler models like SVM or logistic regression. And the third data set is IMDb movie reviews. These are 62,000 movie reviews from different reviewers. These are short texts with an average size of a little bit about 300 words. So with this data set, we want to see, because our approach is a discourse-based technique, we want to see how general it is. Does it work with shorter texts? Right. Originally, we wanted to try Twitter too, but you just can't get any, entity grids out of it. You get 2 sentences. Like what you don't have anything there. So we sort of settled with IMDb movie reviews. So for the baseline, we did very well. Basically, I would say almost solved that task. We're at 99.8%. Accuracy on that data set, 9-class classification. We know that a neural model is definitely works better than previous approaches. We compared it with Feng and Hurst's model. We compared it with SVMs. For the strongest SVMs, we were about 15% higher So that settles it, where neural models are doing well on this particular task. Then on the extended novel task, here we have a 50 class classification with a much larger data set. Supposedly, it should be harder than the previous one. And it is. We got 98.5% to be exact on this data set, but sort of to our disappointment, the SVM also did pretty well on this particular task. Still was at 84, something like that, 85. With more data, it seems like all the models can do better. And in this particular experiments with the large novel data set, we also compared different ways to inject the two types of features I mentioned earlier. So we have grammatical relations, we have RST discourse relations, right? What we found was RST is definitely a more sophisticated method. Basically, using it, we did better across the board in all categories of experiments. We also explored different ways to inject the features, either embedding a feature or just produce one vector as a distribution over features, a simple setup. Giving you an example. Earlier, we talked about grammatical relations, right? Microsoft is the subject in here, an object in second sentence. So for every pair of sentences, we have this transition. In this example, it's a transition from subject to object. So we have SO, right, as a label. So we counted all the transitions. We get a distribution over all the transitions and use that as a feature. This is sort of like a more high-level coarse way to characterize a discourse. In contrast, using RST features, we have a sort of higher resolution to featureize a discourse. Now we know the relations between every pair of sentences. How are they related in different ways? So introducing that, we found that using embeddings definitely helps because we're learning continuous semantic structure. We're learning a semantic space. Also, we try different ways to featureize that matrix. So finally, on the IMDb dataset, just as we sort of expected, the discourse features almost didn't help at all, because these are just too short for us to be able to discover any meaningful discourse structure.
So that's a very high accuracy of predicting who the author is. Can we delve a little deeper on what exactly your model is doing to arrive at these conclusions?
I see. You mean understanding why the model, how the model works, right?
Exactly.
For models, simpler models like SVM or logistic regression, you could just look at the weights on different features to figure out which features are more important than others, right? This is harder for neural models because the features are sort of abstraction. The higher level features in later layers are abstractions on features in lower levels. So it's sort of hard to directly interpret them. Let me first talk about the discourse embedding features. These are explanation. One sentence is one explanation of the other, an interpretation of the other, or an example of a previous sentence. We use the Tisney clustering algorithm to see what are the embeddings we have learned. So a good semantic space where these embeddings live, if intuitively two labels should be close, then they should also be close in the semantic space, right? So intuitively, let's say that you have a label which is background, then the other similar labels to it should be stuff like circumstances, comparison, or elaboration. So in the semantic space, for a given label, we basically extracted top 5 or top 10 nearest neighbors and manually source through them to see if we understand why they are clustered that way. So we found the model does learn a meaningful semantic space where, for example, for explanation, its top neighbors are interpretation, explanation, example, purpose, reason. So intuitively, for a human agent to look at it, it sort of makes sense. We have other examples also listed in the paper.
For many natural language processing tasks, an important benchmark is comparing machine results to human results, because obviously human annotators don't do a perfect job on these things. And we also wouldn't expect that a task like author attribution could possibly be done with, supreme accuracy.
That's a very good question. So I think that usually people would treat human level performance as the sort of gold standard to achieve for, right? Ideally, you do better than human level performance, like the famous squad question answering data set, right? Where the human performance, I don't remember the exact number, but it's high 80 and low 90s sort of level of accuracy. You see machines getting closer to that gold standard, even doing better than that. In that particular task, I think it's fitting to treat human level performance as the gold standard. For authorship attribution, it's a different sort of story. So for this task, in order to classify a text by author, you need to have expertise in the domain. Right, you should be able to know stuff like, oh, this is how Mark Twain would write something. This is how Faulkner writes something. That expertise is very difficult to get from was regular crowdsourcing technique, because the machine usually has large quantity of data to look at. It discovers these little sort of patterns that exist in the data. You would naturally expect it to do better than a human agent without any way to Google or to make use of these world knowledge. So I think it's a tougher task for humans to achieve.
Is there anywhere to go next, or are you hitting kind of a ceiling with your work?
After this project, I started to be supported by a grant by DARPA, where we were tackling a very interesting but also super challenging task, which is semantic inference in narratives. So we call this particular task story salads. So suppose that you have two articles which are human produced by humans. They are assumed to be coherent narratives, right? You break them down into sentences, put them in a jar and shake it. Basically shuffle the sentence. And the task to reconstruct the two clusters of events. So this is basically related to detection of consistent or coherent narratives in conflicting a massive amount of reports on a given topic. In there, we proposed a way to construct a data set large at scale to study the problem for our EMNLP paper. And we tried some baselines, basically the best neural models we could imagine thrown together. That was the larger topic I'm working on. The specific project I'm working on right now, it's also signed by DARPA. So what they want to do is we have this graph of facts, right, or quote unquote facts. In this graph, every event is a node. They're linked in different ways. What they want to do is, given a query, let's say that I'm interested in why this aircraft was shot down. I want to check different reports to see if I would be able to get a consistent or coherent set of facts that would explain the eventuality. So given a query, you find all the related facts to it and cluster them together as an explanation. That's a particular project I'm working on. So for this task is tremendously challenging. All the models that are familiar to us are deep neural nets, which do shallow text processing, right? So what's available to you is you have your distributional patterns in your text, and that's mostly it. You can rely on tools, off-the-shelf tools as Curren Resolution, entity recognition. You could use those. But what I've discovered is human knowledge or common sense knowledge plays a big part in it. So when we present a human being with two articles sort of mixed together, it's usually pretty simple for the human to pull them apart. But in experimentation, we found that we do barely better than random baseline. So if you have 2 10-sentence narratives, you throw them together, the accuracy expectation would be 50%, right? If you randomly do that. We were doing right about 60%. And what we discovered was when 2 narratives are very similar in topic, it's very difficult for a machine to detect that. So we're trying different ways to inject human knowledge in this sort of task. How do you collect human knowledge? How do you featureize human knowledge? So there are different types of human knowledge that could be used in this sort of inference. For example, when you have 2 events, in event 1, somebody ate something. This is the simplest case, right? In event 2, and the person still has that object in his pocket. This wouldn't make sense for any person who can reason. But or if you pour some water on the floor, it gets wet. This sort of thing is very difficult for you to just construct a model and learn from text. So we're looking at the direction of computer vision, trying to see to watch videos and look at images, see what we get from there. And we are also trying to apply crowdsourcing to get humans to give us useful labels for this sort of thing. But you can't, go out and collect all kinds of granular piece of information. On the researcher's part, we have to design a structure for them, for Turkers to fill in the details. So we're in the process of tackling that problem.